So, what if the very foundation of the cloud had a hidden blind spot? Today, we're going to dive into a clever new tool called NecoFuzz. Think of it like a smart locksmith, designed to find flaws that pretty much no one else can see. Let's get right into it. When you picture the cloud, you probably imagine this massive, abstract thing full of servers. But the reality of how it's actually built is way more complex. It's not just one machine, it's layers of virtual machines all running inside other machines. And while this structure is incredibly powerful, it also hides a whole new kind of risk. So, what is this machine inside a machine technology? It's called nested virtualization, and honestly, this Russian doll analogy is the perfect way to get it. You start with a physical server, right? Inside that, a cloud provider runs a virtual machine for a customer. But then inside that virtual machine, the customer can run another one. It really is turtles all the way down. Now, this Inception-like technology isn't just some cool trick. It's actually become a core feature that every single major cloud provider offers. Which, kind of begs the question, why on earth do we need all this complexity? Well, it turns out this layering is incredibly useful. For instance, it lets you run advanced security tools that need their own completely isolated virtual environment. It's also absolutely critical for things like migrating old systems to the cloud without having to rebuild them from scratch, for disaster recovery, and even for creating ultra-secure confidential VMs on platforms like Microsoft Azure. It's really a fundamental building block of the modern cloud. But you know what they say, with great complexity comes, well, a much greater potential for new and really interesting bugs. And this is exactly where we find a new digital blind spot, right in the very foundation of the cloud. See, in the world of security, every new layer of code creates what we call a new attack surface. It's basically just another door or window for an attacker to try and break through. And nested virtualization adds a particularly tricky one. A hidden door that's really, really hard to see. Okay, so let's really break this down. The software that creates and runs all these virtual machines is called a hypervisor. So you got the outer layer, L0, which is the cloud provider's main hypervisor. Inside that, the customer runs their own hypervisor, L1, and then inside that, they run their actual application in an L2 virtual machine. The danger zone, the crucial point of failure, is that complex software interface between the provider's L0 and the customer's L1. That's where the nasty bugs can hide. So if we know this is a risky area, you might be wondering, why can't we just use our standard security testing tools to find these flaws? And that's a great question. It turns out that when it comes to this specific problem, the old methods just, well, they aren't up to the task. One of the most powerful techniques we have for automatically finding software bugs is something called fuzzing. And this locksmith analogy is perfect. It's like you have a locksmith who just tries millions and millions of randomly shaped keys on a lock, hoping one of them will eventually jam it or pop it open, revealing a weakness. Right, so fuzzing has found countless bugs in all kinds of software. So why can't we just point it at this new nested virtualization lock and just let it do its magic? Here's the problem. The key we're trying to use, it isn't a simple piece of metal. The key we need to test this particular lock is the entire blueprint of a running computer, the state of a whole virtual machine. It's not just one little value. It's thousands of settings that all have to make perfect sense together. I mean, we're talking about a complex data structure that's several kilobytes in size with hundreds of different fields that all depend on each other. Trying to guess this with random values is like trying to write a novel by mashing keys on a keyboard. It's just not practical. Most random inputs get rejected instantly, so you never even get to test the deep, interesting logic inside. So because random guessing just won't work, we need a much smarter approach. And that brings us to the solution, a tool called NecoFuzz, the smart fuzzer. And listen, this isn't just some small improvement. The researchers behind it call NecoFuzz the first fuzzing framework that systematically targets this very specific logic. That's not just an iteration, that is a genuine breakthrough. So how does it work? Well, NecoFuzz has three core parts. First, there's a VM harness to run all the tests efficiently. Third, there's a vCPU configurator that explores all sorts of different hardware setups. But the real magic, the secret sauce, is that second part, the state validator. Instead of guessing randomly, it actually reads the official hardware manuals to generate VM states that are structured correctly, but with subtle, targeted changes that are specifically designed to trigger bugs. And this just illustrates the difference perfectly. Let's go back to our locksmith. Random fuzzing is the locksmith just trying millions of random keys.
NecoFuzz is like a master locksmith who studies the schematics of the lock to intelligently craft keys that are designed to test its weakest points. It generates inputs that are right on the boundary between valid and invalid, which is exactly where the trickiest, most dangerous bugs love to hide.
The theory sounds fantastic, right? But did this smart locksmith actually find anything? Let's take a look at the results. A key measure of a fuzzer's success is something called code coverage. Basically, how much of the target program did it actually test? On Linux's KVM hypervisor, the most popular competing tool, syscaller, reached about 61% coverage. NecoFuzz, on the other hand, reached nearly 85%. That's a massive 1.4x improvement, and it proves it's reaching parts of the code others simply can't. But, better test coverage is just a number. The real question is, did it actually find any bugs? The answer is yes. In a very short amount of time, NecoFuzz discovered 6 previously unknown security vulnerabilities. And these weren't in some obscure, rarely used software. These bugs were lurking in the core of widely used hypervisors. KVM, the foundation of virtualization on Linux, the Zen hypervisor, another giant in the space, and even Oracle's super popular VirtualBox. And as you can see from this table, these were not minor issues. They were deep flaws in how the core hypervisor handles the virtual machine's state. You've got bugs found in KVM, VirtualBox, and Zen, affecting both Intel and AMD CPUs. 4 have already been fixed by the developers. 2 were so serious they were assigned official CVE numbers. That's the public catalog for major cybersecurity vulnerabilities. That first bug in KVM, for instance, could allow an attacker to corrupt the hypervisor's memory, a very serious flaw that was only found because NecoFuzz created that perfect, almost valid state that bypassed the normal security checks. So the crucial point here is this. This isn't just an academic exercise. This research directly leads to fixes in the foundational software that underpins the cloud services that millions of us use every single day. It makes that foundation stronger and a whole lot more secure for everyone. The success of NecoFuzz really shows how these new layers of technology can create new, hidden blind spots. And that leaves us with a compelling question. As our technology gets more and more complex, what other critical security flaws are out there just hiding in plain sight?